Hello everyone, welcome back to Calculus BC. We're in lesson number 39 where we're talking about polar equations. In the very first two videos we talked about how to take derivatives of polar equations, and in the next couple of videos we're going to talk about integration and area. So one of the things that we're going to do prior to finding the area of a shaded region given a polar function is figure out where the equation for this comes from. So here's the equation that we're going to be using for the first part of our video, and it's actually derived from the area of a sector that you guys found in geometry. So the equation you guys learned was that n, this is the degree, this was the actual angle that you guys found here, all over 360, and then you guys multiplied that by the area of the circle, right? Because this was the one piece of that circle. Well, we now are going to use radians instead of degrees, so we're going to convert 360 to 2 pi. And notice that then the pi's are going to cancel out here, and you're left with 1/2. You're going to have theta r squared. Well, that's where the 1/2 comes from. So for everything that we do for area, we're going to have pull out of 1/2. We're going to talk about the a and the b in a minute, and then the function squared d theta. So let's actually go and do a couple of questions. You guys can see right now that the thetas, the a and the b, are going to be the thetas that we start with, and then where we end. And then the function is going to be our radius. And so let's actually discuss how we do a couple of examples using this formula right here. So we start with something very basic. It says find the area of the shaded region, and it gives us the graph. And sometimes they're actually going to give us the graph for this. So it's going to give us that r equals 2 plus 2 cosine of theta. You guys can see that this is a cardioid, and so it's asking us to find the shaded region of what you see down here. So a couple of things you have to think about when you're doing these problems. And the first thing is, well, we'll just put 1/2, is, we talked about this back in lesson number 38, that if we look at this cardioid, we know that it's cosine, we know we're going to start right here. So we know that when theta is equal to 0, we're going to get this point right here. So cosine of 0 is 1, so 2 times 1 plus 2 is 4. Then we know that when we come all the way here, we come out right here, well, this is where our function, our radius, is actually going to be 0. So we want to figure out what this value is with this point. You guys know two ways we can think about this. We know that cardioids have a period of 2 pi, and so we're halfway through this, so you know that this is actually pi. Another way you could actually do this problem if you're not sure about the thing is you can actually set this equal to 0. You can actually set the function equal to 0 because this is where the radius is actually 0, right? It's actually at the pole. And then you're going to get that you get -2 is equal to 2 cosine of theta, and then you're going to get that -1 is equal to cosine of theta, so theta has to be equal to pi. And then we're going to go all the way back here to 2 pi. So the a and the b that's represented in this example is going to be where we start. So as we're tracing around our function, our first value that we hit is going to be pi. So we're going to start here at pi, and then we're going to go all the way back around to 2 pi. So we're tracing our shape. And so the a and the b is going to be the thetas that start where our curve is actually started to shade. And then we're going to take our function, which is going to be 2 plus 2 cosine of theta. We're going to quantity square it, and then we're going to do d theta. And most of the time, ladies and gentlemen, these are going to be calculator problems. So when you put this in your calculator, you get 3 pi. So the area of the shaded region here is going to be 3 pi. So let's look at a couple more examples and see what we can do with them. It says find the area of one petal of a rose, and it gives us what the rose is. So one petal of this rose right here. So a couple things that we want to do is just kind of guesstimate a little bit what's going on. Now you don't actually have to know the exact picture for this to kind of figure this out. And it's just ask us for one petal. So the first thing I'm going to acknowledge here is that because it is an even theta, right, even theta, I know that I'm going to have 4 petals. So that's something that we have to kind of think about. If I think about what happens when I plug in 0, right, if I plug in 0, then I'm going to actually start at the pole. So I know that when I go here, I'll be at the pole. I can think about, well, what happens when I plug in pi over 2? If I plug in pi over 2 here for theta, then I'm going to get that the 2's cancel out, and I'm going to be left with the sine of pi. Well, the sine of pi is also 0. So I know that if I'm looking at my first petal, from 0, and then I'm going to come over here to pi over 2. And I want the shaded region of this. And we all know, guys, the fact that I wrote 4 petals here because, if it's an even theta, then you double this number right here. So for this. So if I want the area of one petal, then all I have to do is just find 1/2, and I can integrate from 0 to pi over 2. Right? because again, that's the idea. We also know that because it's an even, we know that the period is going to be 2 pi. So then we can just go 0 to pi over 2. So I just only want 1/4, right? Because I'm one of the petals. And then I'm going to take my function, 4 sine of 2 theta. I'm going to quantity square it, d theta. And so that's how we're going to set up that problem. Now this question you can actually do without a calculator if you want to, because it's, just square this. But we're going to go ahead and save ourselves some time because this video is not how to integrate. It's just actually how to solve the problem. So we get that this is pi over 8. Pi over 8. All right, so the next example we're going to do is find the area of the inner loop. So now we're going to look at the inner loop of our graph for 2 plus 4 cosine of theta. It's really helpful, guys, I think, to actually kind of sketch the graph and kind of see what's going on with it. So if we look at this again, we're knowing cosine. So it's cosine, so we know it's going to be, and it's positive cosine, so we're going to be over here. If we add 2 plus 4, we're going to get to 6. I also know that this 2 right here is going to give me 2 and negative 2. I know that I'm going to be up 2 here, down 2 here. This awesome question tells us that this is an inner loop. So we also know that it's going to be 2. Remember, the difference of the two numbers is going to be where our inner loop is. So we can go ahead and sketch this by knowing that we're going to go this way, and then we're going to come down like this, like so. And the other way that we know this is an inner loop, is the fact that the A is less than B, right? So that was the other questions that we had in lesson number 38. So we want to find the area of this guy right here. So what I want you guys to understand, that's probably the easiest thing to do, is instead of kind of calculating what's going on, remember that I want to start here. So my theta, my little first theta that I want, is what happens when, because remember we start right here. This is when it's at 0, because again, if we plug in 0, we're going to get 6. So what is going to be here? Well, remember that at the pole, our radius is actually going to be equal to 0. So we can solve for cosine here. We can figure out what thetas give us this right here. So that's always the easiest way for me to tell you that. And you could also have set this actually over here for this problem for one second. You can actually have set these two equal to 0 and also found out what thetas would be for that. But let's go ahead and do this. So we're going to get 4 cosine of theta is equal to negative 2. So we get cosine of theta is equal to negative 1/2. So we know cosine is 1/2 for the pi over 3 family. And we know it's actually negative in quadrant number 2, and it's negative in quadrant number 3. So we can do 2 actual problems here. The first way to do the problem is if we can look at the 1/2. We can say, okay, so from 0 all the way to 2 pi over 3. And then we can go back around to 4 pi over 3. And so again, this is composites. So what these thetas are, this A and the B, is like the graph as it's sketching around the shaded region. So like here, again, we go pi, and we go from all the way from pi to 2 pi, we have the shaded region, right? We're touching the shaded region. From 0 to 2 pi, we're touching the shaded region. Here, from 2 pi over 3 to 4 pi over 3, we're touching the shaded region. And then we just go ahead and take our function. We're going to square it, d theta. And now there's one other way you could actually have done this problem if you wanted to, but this is probably the most common way that people will do this, is you could have actually found the half of this. So let me draw like the inner loop looking much bigger. So let's just say, here's our inner loop right here. You could have actually found from 2 pi over 3 and go all the way up to pi. Right? So if you plug in pi to your function right here, you're going to get that the radius is going to actually be 2. So if we plug in pi here, we'll get the 2. It's actually going to be negative 2 because we're going in the negative direction because we're going this way with it. So it's going to go backwards. So what you could do is you could do 1/2, but then do 2 from 2 pi over 3 to pi. So what that means is that I can do half of this. And I'll show you guys examples of where, because this is the easy one, right? I'm telling you right now, the orange one's the easier one, but I'm going to show you guys a couple examples in a future video on why symmetry is actually pretty awesome to do. So if I want half of this, right, then I just do 2 of them. I can do 2 of these versions because I get one from 2 pi over 3 to pi, and then from pi to 4 pi over 3. So I can do the same thing like this, d theta, and it's going to give you the same answer. So this would just be a singleton. And you guys, another reason why I'm bringing this up is that there may be times where you may see the area, like maybe multiple choice, which one gives you the area of, the inner loop of this function. And you may not actually see a 1/2 here. They may actually write it out a different way. So that is the general idea for area. We're going to come back and do some more with these problems because there's a lot of these that we can do. So hopefully this is making sense. And in video 4, I'm going to try to make even more sense with it. So I'll see you guys in the next video. Take care.